Good afternoon, children. Today we are going to start a new chapter, that is haloalkanes and haloarenes. So we'll be discussing the PYQs that were asked in the previous years, and we are going to learn so many concepts. So what you have to do is you have to pause the screen and try the questions all by yourself, and then I'll be explaining the concepts to all of you. So let us begin. So the first question on your screen, I'll become invisible for a minute so that you'll be able to see the question properly. So I'll read out the question for you. Choose the correct sequence of reagents in the conversion of 4-nitrotoluene to 2-bromotoluene. Okay, so I'll be invisible so that you can see the question. Try. Okay, children. So let us see. So what's given to us in the question? It's given 4-nitrotoluene. This is toluene, and fourth position you have nitro. You want to convert it into 2-bromotoluene. Okay, yes. So which one can you think of a plausible set of reagents which can make this conversion possible? If you see NaNO2 and HCl, this is going to cause your diazotization, right? Okay, but for diazotization you need amine first. What do you need? You need amine first, NH2 first. Okay, if there is NH2, that is going to work for your diazotization. So that NH2 is not present here, so this is wrong. This cannot be possible, right? Looking at the other one, this is given SnHCl. Okay, SnHCl is a reducing agent. Okay, if this is a reducing agent, so this will reduce this group and make it NH2. Then you are going to give bromine again. Yes, then you are going to do diazotization. So this is going to become N2Cl, right? N2Cl. Then you are giving bromine with no appropriate reagent with it. So this is not going to convert it into bromo, right? This is not going to convert it into bromo. So this is also wrong. This is also not going to work out for us. Then let us look at the third one. What's happening in the third one? Looking at the third case, the first thing, that is bromination, just Br2 is given, and we know that if we give Br2 this is a electrophilic substitution reaction. So this is ESR, electrophilic substitution reaction will take place, and this is a ortho and para directing group. As ortho para is already substituted, so the reaction is going to take at a single place only. That is going to be your ortho, right, children? Okay, yes. Then okay, then what is the next step? SnHCl, as I said, this is a reducing agent. Yes, children, this is a reducing agent. So let us try giving this to this. So we'll give you Sn and HCl. It will reduce you. So your NO2 is going to become NH2. NO2 is going to become NH2, and then what do you have, children? NaNO2 and HCl you are giving. This reagent is a diazotization. Okay, so if we diazotize this, so what are we going to get, children? N2 plus Cl minus. Then you see children, we're giving H2O and H3PO2. This is an important reagent, as you know that this reagent adds in hydrogen. That means it will remove everything and it will add the hydrogen thing. So this entire thing is going to get removed and here hydrogen is going to be there. So your product will be CH3Br and hydrogen will be here. So this is your what? 2-bromotoluene. 2-bromotoluene, right? So this is going to be your answer, right? So option 3 is going to be the correct answer. Let us look at the last option as well. If we see Sn and HCl, so Sn and HCl is going to convert this into NH2. Okay, no issues. Then we are doing bromination, but what is the reagent for bromination? There is no reagent. Suppose you are doing bromination, so you are doing here. Okay, okay. Then NaNO2 and HCl. NaNO2 and HCl will convert this into N2 plus Cl minus, right? N2 plus and Cl minus. When this converts into N2 plus and Cl minus, you are going to have, this will become hydrogen, right? So you are getting bromine, but you are getting at meta position. You are getting at meta position. So this is also wrong. This is wrong, right? Okay. So option 3 is going to be your correct answer. So I hope everyone understood this question. Let us move on to the next question, children. So next question on your screen, it's giving identify the product of the following reaction. So pause for a minute and try. Okay, so I haven't given any option here so that you can try it properly. So what is the question that is given to us? So we are provided with 1-chlorobutane, right? We're given with this. 1-chlorobutane is being given to us. Now what are we doing? We are giving KCN. Yes, children. So if you give KCN to this, you know that this is a nucleophilic substitution reaction is going to take place, and this is your Rx. Okay, so this will replace your cyanide. So you are going to get nothing but same with cyanide in it, right? Okay, so what are you going to get, children? This is going to get replaced and you are going to get cyanide. So the first reagent is over. Let us look at the second one. Okay, let us look at the second one. What is the second reagent given to you, children? You are given with H2O and HCl. So you are doing the complete hydrolysis and you are heating it, right? So this is hydrolysis. So whenever there is hydrolysis of your cyanide, what do you get, children? You get acids, right? You got acid. Yes. So this one we learned that this is nucleophilic substitution. This is what hydrolysis. Yes, children. Okay. Then what do you have? You see, you have bromine and red phosphorus and water, right? So what are you going to get, children? You are basically going to get here now. See, children, is anyone able to identify that what kind of reaction is this? This both reagents will be taken together, and this bromine and red phosphorus with COOH, it is one reaction, that is your HVZ reaction. What reaction, children? HVZ reaction, which is Hell-Vollard-Zelinsky reaction. Yes, children, this is your Hell-Vollard-Zelinsky reaction. In this part, you attack the Which part? You attack the alpha carbon. Okay, so this is your COOH, so this is our main functional group. Now this is your alpha carbon, this is your alpha carbon, so here your bromine is going to be attached. So what do? You attach COOH here, and there will be one more bromine attached. So this is going to be your final product. Yes, so with each reagent, a concept or a reaction is attached, right? Okay, so that is how we understood how the whole process works and how we got the product. I hope everyone understood it. Let us go to the next question. So next question on your screen, easy one, try it. Okay, so let us see, children, what is given here in this. It's given, there's a compound given to us here. It is an example of what? That is being asked to us. That this compound is an example of what? Okay, so we know that. So we'll see a bit of the classification here. So we'll see about allylic, arylic, vinylic, and benzylic using examples, right? Okay. Okay, so let us look at the 4 examples that we have taken here and understand. So first of all, you need to identify which one is your functional group. Yes, and wherever the functional group it is attached to some carbon, that is going to be our star carbon. Yes. So can I say here, this is the star carbon. In this case, this is the star carbon. Here, this is the star carbon. Again, here, this is the star carbon, right? So we identified our star carbons. So what are the star carbons we are going to consider? Those which have the functional group attached to them. Okay. So now we'll understand each thing one by one. In case of allylic, the star carbon is attached to a carbon. The star carbon is attached to a carbon, or the carbon adjacent to the star carbon has a double bond. Okay. Carbon adjacent to star carbon is having a double bond, right? That is going to be called as your allylic. Yes. Now, if the star carbon itself is having a double bond, that is going to be called as your vinylic. So this one, children, is going to be your vinylic, right? If the star carbon is attached to a benzene ring, if the star carbon is attached to a benzene ring, so this is our star carbon, that is going to be called as your benzylic. If your functional group is itself attached to benzene ring or an aryl group, that is called as your arylic or aromatic. Yes, you can see this is a functional group. It itself is attached to the star carbon. Yes, that is, and that star carbon is a part of your benzene ring. That is going to be called as your what, children? Arylic or aromatic. Yes. So now if we see here, we are going to identify a functional group. Okay. So this is your functional group. This is attached to some sort of carbon. So this is going to be your star carbon. Yes, this is going to be your star carbon. Now this star carbon is attached to, it's having an adjacent carbon. That adjacent carbon has a double bond. So basically this is a which halide, children? This is your allelic halide. Yes, this is your allelic halide. Yes, I hope everyone understood this properly. Okay. Moving on to the next question. So next question on your screen. I'll become invisible. You try. Okay, children. So here we'll discuss certain things first, then we'll see. What is given here? It is given. We'll talk about addition of halogen acids to double bonds. Right? So let us discuss about this. So addition of halogen acids to double bonds. Now if you're having a double bond, you're adding HX. So that rule will be called as your Markovnikov rule. Right? If you have double bond, you're adding HBr, only HBr, in the presence of peroxide. That is going to be your anti-Markovnikov rule. Yes. What happens in case of your Markovnikov rule is a negative part goes to the carbon having less number of hydrogen. The positive part goes to the carbon which has more number of hydrogen. Yes. Now, when you look at carbons, which carbon are you going to look? You are going to look at the doubly bonded carbon atoms. Whenever you're looking, we're talking of the carbon having more hydrogen or less hydrogen. We talk about what? We talk about doubly bonded carbon atoms. Yes. Okay. Now looking at anti-Markovnikov rule, we have two things, positive and negative. Positive goes to the one which has less number of hydrogen. Negative goes to the one which has more number of hydrogen. Okay, so let us see now. So what exactly can happen in this question? Okay, so in this question we are given HBr. Okay, so it's an halogen acid, can be Markovnikov, can be anti-Markovnikov, but here you can see, children, you have been given with benzoyl peroxide. What? Benzoyl peroxide. And we know, children, whenever there is peroxide, there is going to be anti-Markovnikov rule. So now talking of the positives and negative, this is positive here, this is negative. So this is going to go to the carbon which has less number of hydrogen. This will go to the one which has more number of hydrogen. Right? So which two carbons are we going to look? So here we are going to look at these two carbons. Yes. And out of these two carbons, This carbon has less number of hydrogen, that is 1 hydrogen. This has 2. Okay. So the more negative one is going to be attached to the one that has more number of hydrogen. So here you are going to attach bromine and here you are going to attach hydrogen. So what is going to be your final product? I'll write it down. I'll erase all this. I hope you all have noted it down. Okay. So we are going to have yes. So the more one gets the negative part and the less one gets the positive part. Yeah. So this is going to be your major product. Yes. I hope everyone understood. Let us move on to the next question. Okay. Try everyone. Okay. So I hope you all have read the question. The question says the major product formed in the dehydrohalogenation of 2-bromopentane is spent 2-ene. This is based on what? So we are going to study about dehydrohalogenation, which is otherwise called by the name beta elimination. Yes. Okay. So if we talk about 2-bromopentane, so we are having 2-bromopentane here. Now what are we going to do? We'll see that wherever the functional group is attached, that is going to be your alpha carbon here. So this is going to be your alpha, right? We have beta here, we have beta here. Okay, if we removed one hydrogen from here, then this bond would have gone here and this would have gone there. So your product would have been CH3, CH2, CH2, CH, double bond CH2, right? Okay. If we had removed from here, so this would have gone like this. This bond would have come here. And again, this bond would have gone as usual. So you would have got CH3, CH2, CH, double bond CH, CH3. Right? This is pent 2-ene. This is pent 1-ene. Yes? So what is the reason that we got this as the major product? This is going to be the major product. Why? Because there is a rule which is called as SATZIF or sometimes is called as ZSIF. Okay, so whatever you call it. So according to SATZIF rule, that beta hydrogen will be removed, which is more substituted. Which is more substituted means which has less number of hydrogen atoms. Okay, so that beta hydrogen is removed where it is lesser in number. Okay, I hope all of you understood this. Yes, that's why the answer is going to be what, children? Answer is going to be option B, which is SATZIF rule. Yes, so this is dehydrohalogenation or beta elimination, and this is going to be your major product. This is going to be your major product. Yes, I hope everyone understood this. Let's move on to the next question. Next question on your screen and try. Okay, children. So let's see what's given here. It's given here that which of the following alkane cannot be prepared in good yield by Wurtz reaction. So talking about Wurtz reaction, we know that if there is Rx in the presence of sodium and dry ether, we get R bond R plus 2 NaX, right? So here we are talking about symmetrical alkenes. Wurtz reaction is best preferred for symmetrical alkanes. So that alkane, which doesn't have a symmetrical structure, okay, so that one cannot be prepared properly, right? Talking about if there is even number of carbon atoms, that is going to be prepared easily. If there is odd number, cannot be prepared easily, right? So talking about here we have 2,3 dimethyl butane. So the root word has 4, so this is possible. Heptane, now this is 7. This is going to cause an issue here, so this could be the answer. Whereas we'll check the other one. Butane, this is 4, so this is also possible. Hexane, this is 6, this is also possible. Only this won't be possible in good yield. We can prepare by taking 2 different types of alkanes, but we won't get in a good yield. So that's why your answer is going to be N-heptane. Your answer is going to be N-heptane, right? So here we discussed about Wurtz reaction, and you should remember the reagent for Wurtz reaction, that is sodium and dry ether. There is one thing which cannot be prepared by Wurtz reaction, that is your methane, right? CH4, this cannot be prepared. This can't be prepared by Wurtz reaction. And why can't it be prepared by Wurtz reaction, children? Because for children, there is no carbon whose half or whose double is going to be CH4, right? Yes. So this cannot be prepared. Try this. Okay, children. So let us see. Here it is being talked about 2-bromopentane. So this one, children, is a 2-bromopentane. Now we are doing the elimination from pentene, pent-2-ene. So what are we doing here then? We are removing. This is how the reaction takes place. So we are going to get CH3. This is going to be pent-2-ene, right? So we are going to eliminate. So this is our elimination reaction. Just now we had read that what kind of reaction this was, children? This is beta elimination. Yes, this is beta elimination because this children is your alpha carbon. This is beta carbon. This is beta carbon. So from beta we are removing hydrogen. That's why this is otherwise also known as beta elimination reaction. So this option is correct. So A must be there. So A is not there here. So you remove it. First option eliminated. Yes. Follows that safe rule. Yes, we learnt. Why? Because here there is one beta. Here there is other beta. So we are removing the hydrogen from that carbon, beta carbon, which is lesser number of hydrogen atoms. So that is following our SATSIF rule. So this is also correct. This is otherwise known as dehydrohalogenation reaction. This is otherwise known as dehydrohalogenation reaction. Obviously, why? Because this hydrogen was removed because a base was present here. There will be a base, right? The reaction cannot happen by itself. There has to be something which will induce the reaction, right? So this is the base here. So this OH and H will combine to give you H2O. So you are removing water from here. You are removing halogen from here, right? You are removing halogen. So you are removing water. You are removing halogen. That's why this is dehydrohalogenation reaction. Is it only dehydration reaction? No. This is not dehydration reaction. Dehydration leads to formation of alkene. So D should not be there. D should not be there. Yes. So your option D is going to be the correct answer. Yes, wherever D is not there, that is going to be the answer, and it's present in option D. So that is your answer. Yes, I hope everyone understood this. Yes. Okay. Next question on your screen, children. Try. Okay, children. Did you all try it? So it's given. This reaction, children, what kind of reaction is this? This is your substitution reaction, right? This reaction is a nucleophilic substitution reaction. Now we have to find out that what kind of mechanism that does it follow. So for that we can decide from the degree, right? This is 1 degree. So most likely under normal conditions, this is going to undergo SN2 reaction, right? And here we are talking about solvents. We're talking about solvents. So these all are your solvents, right? And SN2 works the best in polar aprotic solvent. Ethanol is a protic, methanol is a protic, water is a protic. Only there is one which is polar aprotic, and that is your DMF, right? So this is your children polar aprotic solvent. Yeah, so this is going to be the best. This is going to be the best in case of your solvent, because this reaction is following which mechanism? SN1 mechanism. Sorry, SN2 mechanism. If it were SN1, then this is going to be the worst one. Why? Because they need polar protic solvent. Yes. Okay. Okay. Okay, children. Let us move on to the next question. So this is your correct answer. Okay. Now here there is a question. I'll write down the question here. Which of the following is chiral? Okay. So this is a question. Try everyone. Okay. So talking about chirality here, in case of biphenyls, how do you decide which one is chiral? So your answer is going to be A here. I'll tell you why. Because in case of biphenyls, what are you going to see, children? You have to see that whether they are in the same plane or not. Okay, you have to see that whether they are in the same plane or not. They should not be in the same plane. They should not be in the same plane. Yes, they should not be in the same plane, and such that when you take their mirror images, they should be non-superimposable. Yeah, so you can see those who are saying D is not the answer. Yes, D is not the answer. Okay, so option 1, because they are not present in the same plane, whereas the rest of them, they are present in the same plane. Okay, they are present in the same plane. That's why, children, A is going to be your correct answer, because this is not present. The ortho substituted products, they are not present in the same plane. Okay, so that is going to be the correct answer. Okay, so next question on your screen. So what's the answer, children? The answer everyone knows that this is going to be option 1. We'll discuss that why this happens, right? Why does this happen? Let us see. We are talking about SN1 reaction, children. We are talking about SN1 reaction. We know that SN1 reaction involves carbocations, right? They involve carbocations. And what is the shape of a carbocation, children? The shape of a carbocation is planar. We know that it is sp2 hybridized. That is, this is how your planar carbocation looks like, right? So what happens, children, when it looks like this? Your reagent can attack from front. Your reagent can attack from back. Okay, this is back. So there can be inversion, there can be retention because of this when there is front side attack. Yes, back side attack, it will lead to inversion. So there is both inversion and retention, which leads to racemization. Which leads to racemization. Which leads to racemization. But there is one thing that you need to know here. Okay, there is one thing that you need to know here, that is, in case of SN1 reaction, the rate depends on how much shielded is the front side. How much shielded is the front side. Okay, it depends how much shielded is the front side, right? Okay, so when the front side is shielded, so definitely what is going to happen, children? Your inverted product is going to be more, a little bit more. Your inverted product is going to be little bit more. So that's why we said there is little bit of more inversion, then retention, leading to partial racemization. We cannot say that there is complete 100% racemization. We are going to say there is partial racemization where inversion exceeds your retention, right? Okay, so this is what we discussed. Yes. So these were few of the important questions and concepts that we have dealt here. Yes. So in the next class, we'll come up with some more concepts relating to organic chemistry. So now we are continuing the organic chemistry series here. Okay. So next class we'll be continuing that. So until then, take care, children. Bye bye and keep reading.